Hello, I'm really excited to introduce to you today a brand new technique which we believe is going to recharge your lithium research. It's based on work initially done at the Austrian Institute of Technology, but is being commercialized by Gatan and EDAX. Now, lithium compounds and alloys have very significant applications in our 21st century world, whether that's lithium-ion batteries used in electric automotive vehicles or mobile electronic devices, or as lightweight structural alloys in the aerospace or automotive industries. These are of important commercial value, but perhaps more importantly, further developments and greater adoption in these technologies are absolutely critical in meeting the energy reduction plans that our governments have set out for the next 10, 20, 30 years. Now, electron microscopy is a key characterization tool already in these market segments, used both in research and development and also failure analysis, whether that's analyzing the structure of lithium-ion batteries, looking at the interfaces between the electrodes and the binder and separator, or just characterizing the distribution of particles within a cell, or in lightweight structural alloys, revealing the microstructure, the grain orientation that is present in a material after processing. Both of these are absolutely important to controlling the properties and the performance of the devices and materials that are made using these materials. However, an inability to map lithium distribution in the scanning electron microscope presents a really major obstacle in driving these technologies forward. That is until now. As you can see on the bottom left-hand side, in colorized in pink, we have a lithium map collected from a lightweight structural alloy. Now, before I go into any detail about what this map is and how we collected it, I want to take a step back and remind you of the lithium problem in the scanning. Now, elemental distribution in a material or a device at the microscale is typically determined using a technique called energy dispersive spectroscopy, so EDS. And in this technique, the electron beam of an SEM generates an X-ray fluorescence from a sample. And typically the energies of those X-ray photons are characteristic of the atom which produced it, allowing us to generate elemental distribution information from the point that we've analyzed, and then by scanning an array of points across a specimen to generate these maps of the elemental distribution, like we see on the left-hand side. The technique has high sensitivity and specificity with submicron spatial resolution and can be quantitative. So the map on the left-hand side is a magnesium, lithium, aluminium or aluminum alloy. And one of the key takeaways from this map that you should see is that although we can identify the presence of magnesium and aluminum, also carbon and oxygen, there is impurities, we are unable to see lithium using EDS. And it's not just this particular alloy system where this is a problem, but in almost all commercially important materials, it's not possible to identify the presence of lithium by EDS. So first of all, there's no guarantees that lithium X-rays are actually produced by a specimen that contains lithium. The X-ray energy and its fluorescence yield depends on the lithium bonding state. So in some materials or compounds, it's just a law of nature, a law of physics, that no lithium X-rays will be generated because of the bonding state of the sample. Now, when lithium X-rays are generated in a sample, they're also readily absorbed prior to reaching the EDS sensor because they have very low energy. This means that they can be readily absorbed by surface contamination, presence of carbon, hydrocarbons on the surface of the sample, or an oxide layer, for example. Now, some specialized lithium detectors have been commercialized. They have a limit of detection of about 20 weight%, or equivalent to about half the atoms being present in a sample. But remember, importantly, there is no guarantee that lithium X-rays are produced in the sample, even if your sample contains lithium. Often the only way that these detectors work to detect lithium is by actually changing the bonding state of the lithium, damaging the specimen to liberate metallic lithium, and then analyzing the X-rays generated from the damaged sample. Now, obviously, this doesn't give you any information about the native state of your sample. It's only the state after it's been changed. So this is, in a snapshot, the lithium problem in the SEM. So as I mentioned at the beginning, researchers at the Austrian Institute of Technology developed a brand new method termed the composition by difference method. And this type of analysis is actually well accepted in chemical or chemistry, in chromatography, for example, or other chemical analysis techniques. And this composition by difference method uses two different signals, which you can quantify, and then compares them to work out what is missing. So in this approach, we take the backscattered electron signal, which depends on all elements, and we quantify that. This allows us to determine the mean atomic number of a region of interest that we're analyzing. From the same region of interest, we also collect the EDS signal. And from the EDS signal, that allows us to quantify the non-lithium elements within a sample. So we have these two different data streams, which we collect using the OnPoint backscattered electron detector from Gatan and the Octane Elite or Elect Super EDS systems from EDAX. And by comparing these two data sets, we're able to extract the lithium content, which is missing from the EDS signal. Now, this technique, this composition by difference method, has been verified by an external accredited laboratory using glow discharge optical emission spectroscopy. And in that comparison of the results generated by the composition by difference method and the external laboratory agreed to within approximately 1 weight%, so very good accuracy. And using this technique, this information provided by the backscattered electron signal and the quantitative EDS analysis, that allows us to generate and extract these lithium maps from samples. So in this magnesium lithium aluminum alloy, we're able to generate single-digit weight percentage maps of lithium mapped quantitatively in the SEM using the composition by difference method using the Octane Elite Super EDS detector and the OnPoint backscattered electron detector. I hope you agree that this is a really exciting development for the characterization of lithium compounds and alloys, and agree with me that it will really empower you to recharge your lithium research. Thank you for listening.